as we keep learning about enumerative combinatorics, or fancy ways of counting things, the next thing we're going to talk about are partitions. Remember that a partition of a set is a family of sets, in other words, a collection of sets, A sub I, so that the AIs are disjoint from one another. There is no element that belongs to two different sets, but also the union of all of the sets will reconstitute A. So overall, you split the set A into a collection of sets that are all different from one another, but you did have to use all of the set A overall. So now we're specifically going to be concerned with counting how many ways there are to partition a set of K elements into different subsets. So if I have K elements all together, I want to partition that into different subsets, and we're going to count how many ways to do so. Now, the empty set could always be added into a family of sets any number of times without affecting disjointness, because the empty set intersect anything would be empty again. So the empty set is disjoint from everything, and it also won't affect the overall union because you're not adding anything into the collection. So since we could always add the empty set over and over and over again, we're actually going to require that the sets we use be non-empty. Otherwise, you run into a problem of having infinitely many ways of doing things, and you wouldn't really have counted anything. So the sets that we use for a partition are always going to have to be non-empty. What we're going to do is we're going to consider the elements of the set A as labeled balls, and the sets we construct are unlabeled bins. A set containing two elements doesn't have a label on it except for what the elements are. So the elements have labels, those are the balls. The bins as the sets are not themselves labeled. So two sets can be told apart based on what elements they have, but any two sets with the same element are the same set. So the bins are not labeled, but the balls are. All right, so for example, suppose we have three elements, A, B, and C. We can make the following partitions. Either the partition just has the entire set, or maybe we partition it into two sets where A and B belong to the first set and C belongs to the second. Or maybe A and C belong to one set and B belongs to the second. Since the elements of the set A, B, C are all labeled, these are different from one another because I can tell a two-element set AB is different from a two-element set AC. It's also different from a two-element set BC. So all of these are different partitions, even though they all are partitions into a set with two elements and a set with one element. Because the elements of those sets are labeled, these are all distinguishable. And this is a whole other arrangement of three sets, each with a single element. So with three elements, A, B, C, in our set A, there are 5 different ways of making a partition. We're now going to introduce what are called Stirling numbers of the second kind. Yes, there are Stirling numbers of the first kind, but we're interested in these ones. Stirling numbers of the second kind count the number of distinct partitions of n elements into specifically k non-empty subsets. And we use this notation. It's very similar to binomial coefficients, but instead of parentheses, we have braces. You simply call this the Stirling number of the second kind, n over k. So on the previous slide, we observed a few things. The Stirling number of the second kind, 3 over 3, is 1. There is only one way to partition a set with 3 elements into 3 distinct non-empty subsets. You have to put each element into its own set. But there are 3 distinct ways of partitioning 3 elements into 2 in different subsets. Remember, there was AB and C versus AC and B versus BC and A. Okay? Ultimately, if I want to partition 3 elements into 2 subsets, I'm simply choosing which element goes into a set by itself compared to the other 2 elements going into a set together. So there were 3 distinct ways to do this. So the Stirling number of the second kind, 3 over 2, is 3. And how many ways can I partition a 3-element set into a single set? There's only one way to do it. You just use that set as the only piece of the partition. So the Stirling number of the second kind, 3 over 1, is just 1. There's a single way to partition 3 elements into one set. We're going to derive a way to compute these numbers through some recursive properties that we have to carefully construct. So here are our initial observations about Stirling numbers of the second kind. So some of them are actually pretty easy to derive. The empty set can't be put into any partition. So how many ways are there to partition the empty set into non-empty subsets? 0, definitely. Remember, the number on top is how many elements go into the set. The number on bottom is how many non-empty subsets we're using. So how many ways to put no elements into k different non-empty sets? Well, since these have to be non-empty sets, it simply can't be done. So Stirling numbers with 0 as the top argument are always 0. We also cannot partition a set into 0 non-empty subsets. If I have n elements to distribute and I want to use 0 sets, that also can't be done. So if the bottom argument is 0, the Stirling number of the second kind also computes to be 0. Now what if k is larger than n? In other words, the bottom argument, which is the number of non-empty subsets, is larger than the number of elements to use. Well, that also cannot be done. If I only have n elements and I have more sets that have to be non-empty, that can't be done. So if the bottom number is larger than the top, the Stirling number of the second kind is also 0. So we have a whole bunch of scenarios where the guaranteed result is 0. If the top argument is 0, if the bottom argument is 0, or if the bottom one is simply larger than the top one. Now what if the number of elements to distribute is bigger than or equal to 1, and I only want a single set? Well, since I'm only using a single set, the only way I can do that is to put all of the elements, all n elements, into one single set. So as long as n is bigger than or equal to 1, as long as there's actually elements to distribute, the Stirling number of the second kind with a 1 on the bottom will always be 1. There is a single way to put some positive quantity of elements into a single set. You simply put them all into it. Similarly, what if you have elements and I have exactly that many sets to use? So I want to place n objects into k sets. All the sets have to be non-empty. So I want n elements into k non-empty sets, but that's also n non-empty sets because we're assuming here that k is equal to n. Well, if I have n objects into n non-empty sets, you sort of quickly see the only way to do this is to put every element into its own set. Since there's only one way to do that, everything gets its own set. If the two numbers are equal to one another and are not 0, then the Stirling number of the second kind is also 1. So if either argument is 0, there's no way to do this. If the bottom argument, the number of sets, is larger than the number of elements, since we are only using non-empty sets, there's no way to do that. If I want to put a positive amount of elements into one set, there's one way to do that. But if I want to put a positive number of elements into exactly that many sets, there's also one way to do that. So we've made some initial observations about extreme scenarios to compute Stirling numbers of the second kind, if there are zeros involved, or if numbers are really specific, like the two arguments are the same, or the bottom argument is 1. But how are we going to compute Stirling numbers of the second kind for some intermediate values of k? Remember, if k was equal to 1, there's only a single set here, so I put all elements into that set, and that's fine. And if k is equal to n, I have to put every element into its own set. But what about intermediate values? So we're going to develop a recursive identity that's going to look a lot like Pascal's identity. Suppose we've already determined a whole bunch of Stirling numbers of the second kind. Specifically, all of these m's up to and including n, and all of these numbers of sets up to and including k. So now we're going to try to determine the value of new Stirling numbers of the second kind by letting the number of elements increase to 1 larger, to n plus 1, or possibly the number of subsets will increase to 1 larger. Okay, if we've already determined how to do it for all numbers of elements up to n, then letting the number of elements go up to 1 larger would be n plus 1. And if we've already accounted for a number of subsets up to and including k, then one more subset allowed would be k plus 1, or maybe we'll do both. We don't actually need to do both simultaneously. Okay, if I can figure out how to increase the number of elements, but then I can also figure out how to increase the number of sets as 2 separate steps, I just do one and then the other, and we've managed to increase both of them. So first, let's see, how can I distribute n plus 1 elements into k non-empty sets? Well, we know that if I want to put it into a single set, there's only one way to do it, so let's assume the number of sets is at least as large as 2. We're going to do a similar trick that we've done before. Out of the n plus 1 elements, consider one element to be special and the rest to be regular. So now I want to distribute n plus 1 elements into k non-empty sets, and one of these elements is special. Well, there's two possibilities. Maybe the special element goes into its own set, or maybe it goes into a set along with something else. Okay, so continuing, we're distributing n regular elements and one special element into at least two subsets. If the special element is given its own subset, all the rest of the regular elements have to go into all the rest of the sets. So out of n plus 1 elements, one was special, so n are regular. And out of k subsets, one of them is given its own subset, just the special element, so there are k minus 1 remaining subsets to use up the remaining n regular objects. Well, that's exactly this Stirling number of the second kind. There are this many ways to do that. And remember, inductively, we're assuming we know this value. But what if the special element isn't in its own subset? Well, then all the rest of the regular objects are partitioned into all of the subsets, all k of them. And there's exactly this many ways to do that. But for each such partition, we have to pick which subset the special element is going in. All we've done is assume the special element is not by itself, but we haven't actually specified which set it goes into. So since there are k subsets to choose from, however I partition those n remaining elements into k non-empty subsets, I get to pick which one of them gets the special element. So that's a two-step process. First, distribute the n elements into k non-empty subsets, and there's this Stirling number of the second kind quantity ways to do that. Then pick which subset gets the special element. Well, there were k subsets, so pick one of them. There are k ways to do that. Overall, there are k times that Stirling number total ways to partition the n regular objects into k non-empty subsets, and then choose which of the k subsets gets the special object. So overall, we've determined how to distribute n plus 1 objects into k subsets. As long as the number of subsets is at least 2 and the number of objects is at least 1, we can either distribute the special element into its own subset and then the n elements that are not special into k minus 1 subsets, or we can distribute n special objects into k non-empty subsets and then pick which of those k subsets gets the special element. So overall, this Stirling number, n plus 1 over k, is the sum of the Stirling number of the second kind, n over k minus 1, plus k times the Stirling number of the second kind, n over k. This is very similar to Pascal's identity, except for this multiplier of k. If this weren't here, and these were binomial coefficients, it would just be Pascal's identity. But the similar-looking identity for Stirling numbers of the second kind multiplies this by k. And now we have a recursive identity that we're going to be able to use to construct and compute larger and larger Stirling numbers of the second kind. So let's compute some. So between the extreme cases where the Stirling number of the second kind was easily seen to be 0 or 1, we combine that with this Pascal-like identity that we derived on the previous slide. Now we're going to compute some values, although I'll admit it does take a bit of work. So for example, let's try to compute the Stirling number of the second kind 5 over 3. If I have a set with 5 elements and I want to partition it into 3 non-empty subsets, how many ways can I do that? Okay, let's apply the Stirling identity, like Pascal's identity. N plus 1 over k can be replaced with reduce both arguments by 1. So 5 over 3 gets replaced with a 4 over 2, plus whatever that bottom argument was, 3 times, reduce the top argument, but don't reduce the bottom. So 5 over 3 becomes 4 over 3, but that's being multiplied by the bottom argument 3. So the Stirling number of the second kind, 5 over 3, is 4 over 2 plus 3 times the Stirling number of the second kind, 4 over 3. Now this can itself be reduced down to this quantity right here, using the same process, reduce both arguments, or multiply by the second argument and only reduce the top argument. Similarly, factoring this 3 out, reduce both arguments by 1, but then add the bottom argument times only reduce the top argument. Now we can start making some simplifications. As soon as we see ones down in the bottom, we know we're in business. How many ways can I partition 3 elements into a single set? One way. So this Stirling number I can simply replace with 1. Here I'm factoring the 2 out and saying instead of the Stirling number 3/2, reduce arguments by 1 plus bottom argument times reduce only the top argument by 1. Okay, now I've got this 3 factored out here. This Stirling number 3/2, I'm doing the same thing. Reduce both arguments by 1 plus bottom argument times only reduce the top argument by 1. Now in here, we've got a Stirling number 3/3, and we've observed that when these two numbers are equal, the result is 1. So this becomes a 3 times 1. All right, continuing. Whenever the bottom argument is 1, there's one way to do it. Whenever the two arguments are the same, there's one way to do it. Whenever the bottom argument is 1, there's one way to do it. Whenever the two arguments are the same, there's one way to do it. And finally, we just have a whole bunch of numbers. 25. So overall, how many ways can I partition 5 elements into 3 non-empty subsets? There are 25 ways to do it. This is actually a lot faster, even though it doesn't feel like it at first, compared to doing something like, well, maybe I have 5 elements all in one set. And now I try to laboriously compute, well, what if I put 4 elements into a single set and 1 element in its own set? Okay, well, now I have to pick which thing gets its own set. So I could have also done this. Or I could have done this. Maybe C is the element that gets its own set. Okay, clearly I'm going to have 5 ways of doing this because I'm just picking which element gets its own set. But this was specifically only accounting for a set of 4 elements and a set of 1 element. Well, since I have 5 elements to distribute, what if I had a set of 3 and also a set of 2? Now I have to go about and compute how many ways I can put 2 elements here and 3 elements here. Okay, that's doable, but what if I didn't have a 3 element and a 2 element? What if I had a 3 element set and a 1 element set and a 1 element set? That's actually different. I'd have to count all the ways of doing that. What about all the ways of doing a 2 element set and a 2 element set and a 1 element set? What about all the ways of doing a 2 element set and a 1 element set and a 1 element set and a 1 element set? This is starting to get out of hand. Okay, so it's actually faster to use this identity here. This allows us to continuously reduce arguments of the Stirling number that we're computing. And eventually you'll get down to 1s on the bottom, which can be replaced with a 1, or the two numbers being equal, which can also be replaced with a 1. But wouldn't it be nicer if we simply had an explicit formula? The good news is we do. Suppose n and k are 2 natural numbers. Specifically, n is positive, and k is something in between 1 and n. In other words, the Stirling number is not going to be trivially equal to 0. Well, then we can compute it with this formula right here, which, as complicated as it looks, is definitely less work than always going through the process we did on the previous slide, and is certainly less work than actually trying to figure it out just by partitioning things. So we have 1 over k factorial, where k is the number of non-empty subsets we're using. We then take a sum going from 1 to k. We have powers of -1. These are now binomial coefficients and powers of I, where I is this index of summation. So in fact, binomial coefficients buried underneath a sum with powers of -1 and powers of numbers divided by another factorial can be used to compute Stirling numbers of the second kind. I can't just say that though, we have to actually prove it. So this theorem can be proved by verifying a certain collection of things. It does predict that if k and n are the same number, we get out a 1. So here I would have an n factorial. Here I'd have a sum going all the way up to n. This would be an n, this would be an n. Okay, it does take some work, but you can simply verify that if k is equal to n, this always spits out a 1. For example, you can induct on n. You can also say, well, what if k is 1? This is easier, okay? Because now I simply have a sum going from 1 to 1. There's only a single term in there, in which case the only choice for k is 1, the only choice for I is 1. So I'd have negative 1 to the 0, I can ignore that. The only choice for k and I is 1. 1 choose 1 is 1, and 1 to the n power is also 1. So I get out a 1 here. So yes, if k is equal to 1, this formula predicts the correct response. And then this formula on the right-hand side verifies the same identity that the Stirling numbers of the second kind do. So in other words, and again, this takes work, but you can show it, okay, just by writing out this sum for n plus 1 and k, writing out this sum for n and k minus 1, and writing out this sum for n and k and multiplying it by k. And you'll see that you can combine all of these terms to get out this one. And it's no surprise that because there's binomial coefficients here, Pascal's identity will be useful. Okay, it's a bit longer than I want to spend the time to do, but just observe, the formula predicts correct values at the extremes, and using this identity here, it can then be used to compute correct values on the intermediate values. So since it matches the starting values, where there's a 1 on the bottom, and this recursive relationship, it must actually match everything in between. This is a common combinatorial trick. If you can find a formula that does something correctly and matches the same recursive formula, then it will match values forever. So since this formula can be shown to match starting values and the same recursive formula, it will continue to match values. Okay, but as I said, we're really not going to get into the proof of this. We're just including this formula for interest. It takes quite a while to establish, especially this and this. So I just want to point out, there is a formula for computing Stirling numbers of the second kind. At this point in your mathematical careers, it's enough to just know the formula exists and where to look it up when you need it. We conclude with another bin sorting problem. The number of ways to distribute n-labeled balls into k unlabeled bins, as long as no bin is allowed to be empty, is given by these Stirling numbers of the second kind, n over k. But if the bins are labeled, the total number of such distributions is just the same thing multiplied by k factorial. Well, we've already remarked that if the bins are unlabeled, they're really just functioning as subsets. You're putting certain things into a bin, in other words, putting them into a set. But what if the bins have labels? Okay, then for any partition into k unlabeled bins, we can in fact label each bin with the numbers 1 through k. So I have k distinct subsets, and I just want to label them 1 through k. But if I imagine the bins placed in a row, there are k factorial ways to put the labels onto the bins. Okay, if I want to distribute the labels 1 through k onto the k different bins, there are k factorial ways to do that. So the total number of distributions is first distribute into bins, that's the Stirling number, n over k, and then assign labels to the bins, and there are k factorial ways to do that. So this product is exactly the number of ways to distribute n labeled balls into n labeled bins on the restriction that no bin is allowed to be empty.